So the other day, on my way to work, there was this guy who was playing the trombone. It made me think about all the amazing physics that goes into musical instruments in general. So today, let's talk about resonance. So, resonance. What is it? Well, strictly speaking, it's about when energy causes a wave to form and often grow. So what do we mean by that? Well, that energy could come in the form of another wave. For example, have you ever seen it when there's a car driving by on the road and they have a really loud speaker and they come through and they cause your own car, to start shaking? Well, that's a form of resonance. Or maybe if you've been in like a band, and then somebody like a French horn plays a note, and then you notice the bottom of a drum starts to vibrate and makes a little bit of sound. That is also a form of resonance. Now, strictly speaking, we need to be careful because there are three types of resonance that we're going to need to know. We're going to need to know something about when a tube is open on both ends. So an open tube on both ends is going to be the resonance that happens in many types of musical instruments. Lots of wind instruments are going to be here because they're open on both ends and they're basically a tube that goes from one side to the other. So most of your wind instruments are going to be in that category, with one big exception of families. Then there's going to be a tube, open, if I could write, on one end, and closed on the other. So, the classic example of this is that there's a whole family of things. They are called flutes. And flutes in general tend to have one side that is closed, one side that's open. You can even see some of those, like the South American pan flutes. They're open at the top and closed on the bottom. But even just blowing across the top of a tube of, or across the top of a water bottle or a Coke bottle will give you that sort of resonance. And finally, we're going to have a tube that is closed on both ends. Now, obviously, you ask me, how do you put energy into that thing? Well, it doesn't necessarily have to be a tube. Sometimes it could be a string that is fixed on both ends. And so a lot of your string instruments are going to fall into this category. So most of the orchestra, guitars, pianos, all of those are going to fall into this category. And percussion instruments can sometimes be this category too. Tubes closed on both ends and you bang on one side of it. Sometimes they're open on one side, and that would put them in the same family as flutes. Now, does this make a difference? Does the type of resonance make a difference? Well, take a look and see. I'm going to have here a piece of PVC pipe, and I'm just going to blow across the top of it. Sometimes I'm going to keep one side or the other side open, and sometimes I'm going to use my hand to close off the bottom. See if there's a difference. Okay, so what about the other two possibilities? What about where it's fixed on both sides or when it's open at both sides? Well, it turns out there's some similarity to these. Because let's imagine, for instance, we have a string. Maybe it's a guitar string. And it's fixed right here. And it's fixed right here. So imagine you have a guitar string that is stretched sort of like that. Okay, so now that you have that string, you decide to pluck that string, and what's it going to do? It's going to vibrate. But it's pretty obvious what's going to happen. It's going to vibrate by bulging out this way for some time, and then at some other time it's bulging out that way. And if you look really closely after you pluck this guitar string, you'll see it vibrating back and forth really quickly like that. This again is the fundamental mode. And the fundamental mode of this is going to be given by, well, if you go back up here and you look at how we had our waves showing up, we're looking at, this diagram is getting a little bit messy, but we're looking at from here to here, which is half of a wavelength. So likewise here, we have half a wavelength. You could complete this wave by drawing something over here, right? But so we have half a wavelength here. So for this one, L is going to be equal to lambda over 2. Now, in theory, you could make this wave do something else. And if you've ever played a guitar or even some of the orchestra instruments, some of the string instruments, they have something that they know of called harmonics. And in order to do that, so this is a harmonic, what would you need to do? Well, you put your finger very lightly on the string, somewhere around there. And if you put it in the right place, you will notice that your wave is now made to do something like this, where you have it going. So your finger's right here. That should have been kind of centered, but your finger's right there, and you hear a lot higher pitched frequency from that, a lot higher pitched sound, because those waves are a shorter wavelength. Okay, so in this case, how much of a wave do we have? Well, you can tell we have one up and one down at any given time, so L has to be equal to lambda. Okay, and then finally, over here, we have, well, we could do, instead of having just 3 nodes, we could have like 4 nodes that this passes through. And we could have a wave that looks sort of like this at one time, and then at a different point in time it's doing this. And so now we have, well, that's 1.5 waves, so L is going to be equal to 3 lambda over 2. Okay, so you might start to notice something. That in this case, what's the pattern? We're increasing by halves. We have lambda over 2, we have lambda, 3 lambda over 2. The next one would be 4 lambda over 2, or just 2 lambda, and then 5 lambda over 2, and so on. So what is the pattern that we have here? Well, it's going to be n lambda over 2. That has to be equal to L. And n is any integer. Okay, so what about something that's open at both ends? What about some sort of instrument, or your brass instruments, your flute, or your clarinets, your saxophones, all of those things. Most of the wind instruments in general are open at both sides. So what goes on in those cases? Well, again, it's going to be something like this. So imagine you have a tube, like so. And we need to fit a wave into the tube. And we know that at the edges, at the ends here, there's got to be an antinode, a big open space. This has got to be bouncing around. So because we know that both of these ends have to be bouncing around like crazy as antinodes, we know there must be a node in the middle. So because of that, it must look something like this in its fundamental mode, where you get a wave that forms sort of like that. So this is the fundamental mode. And over here, if we think about it, from here to here is a quarter wavelength, and then from the center over to here is another quarter wavelength, so L is equal to lambda over 2, which is starting off kind of similar to what we saw before. Then the second way we could do this is if we had, instead of one node, we could have a couple nodes in here. And then it would be doing something kind of like this. And L is equal to, all right, so we've got half a wavelength here. We've got a quarter there and a quarter there. I didn't draw that. That should have been a lot bigger in the center. So lambda is equal to, it's just lambda is equal to L because we have 2 quarters plus 1/2 is 1 full wavelength. Okay, and then as we go on to the next one, in theory, we could have another node in here. So we could have 1, 2, 3. Wait, I only have 2. Should be 3. Okay, 1, 2, and 3. And then it would look something like this. And over here, and now you can see there's one wavelength in between there. There's a quarter here and a quarter there. So 1 plus 2 quarters is 1.5, or L is equal to 3 lambda over 2. And now you can start to see that this is actually following the exact same pattern that is given by the string instruments. L is equal to n lambda over 2. Lambda over 2, lambda, and 3 lambda over 2 is the exact same pattern. So for this is correct as well. L is equal to n lambda over 2. Again, where n is any integer. And in fact, this explains a lot of your brass instruments. When your instrument resonates in this fundamental mode, it's the lowest note you can play for that fingering. So what does that mean? These are what we often call pedal tones. And then here and here are going to be harmonics. This one, it turns out, this first harmonic is going to be, 1 octave exactly above the fundamental. And then way down here, this is going to be, I think it's a 5th above. So if this ends up being something like a B flat, this will end up being a B flat also. And then this ends up being an F. And then as you keep on going up, you can keep on getting more and more higher pitched notes as you go to higher harmonics. The only thing is, it takes more energy to produce those sorts of waves. And so you have to do things like have really fast air, and you have to tighten up your embouchure, and you have to buzz really quickly. And the higher you go, in theory, there's no limit to it, but it gets harder and harder to do the higher you go. Take a look at this, for example. So, let's see what happens in an example. What if you had something like this? Let's say somebody tells you, you want to blow across the top of a bottle and produce an A, the note A. How much water should you put in the bottle? Okay, so we'll have let's have I don't know, maybe a Coke bottle type thing here. And all right, so here's our bottle. And we're just going to blow air across this. That's going to provide the energy for a wave to form inside that bottle. Now, we know since it's open at the top, this is going to have to be an antinode. And since it's closed at the bottom, this is going to have to be a node. Okay, so in its fundamental form, that's the easiest way to do this. We know that that part is fixed, and it's going to open up into a wave that sort of goes like that. So again, this is closed on one side, it's open on the other. So this is going to follow the form of L equals N lambda over 4, where N is odd. Okay, well, in the fundamental mode, N is going to be equal to 1. So L is equal to 1 times lambda over 4. The only problem right now is that we don't know what lambda is, but we are given this thing about the frequency of A, about the pitch of A. And we know that the frequency of A is going to be 440 hertz. That's a middle A. Turns out that frequency might be ridiculously large for this size, but we're just going to go with it and see what happens. We might have to increase the frequency up an octave. If we do go up an octave, it's actually a pretty easy thing, and we might have to increase it to 880 hertz. And each time we double it, that'll be 1 octave above. So this would be middle A, this would be high A, and then another one would be an octave above that. Okay, so we know the frequency and we know the speed of sound in air. It's going to be 343 meters per second. Okay, so let's see here. We know V equals F lambda. So I'm going to solve this for lambda. Lambda is equal to V over F is equal to 343 meters per second divided by 440 hertz. And grab our calculator. And let's see here. So it's going to be 343 divided by 440, which means the wavelength is, I get 0.77954545. Let's call that approximately 0.780 meters. Okay, so 0.780 meters is going to be our wavelength. The length of this tube should be equal to, it's given back up here by this, and I can get rid of the 1 because it's not really doing anything. So L is going to equal lambda over 4. This is equal to 0.7780 meters divided by 4. That's equal to, and I'm going to use the exact number here when I divide, and I am going to get 0.19, call it 5 meters. So 19.5 centimeters is how big this thing needs to be. But we need to be careful. Remember that where is it resonating? In the air. So if we have our bottle here, and I'll draw it a little bit bigger so we can see exactly what's going on here. Okay, so here's our bottle. Pretend that's nice. Pretend that's symmetrical. And the wave is going to be inside this bottle. But we're putting water in it to make sure it's the right height. But the height is not going to be measured of the water. We don't care about how much water's down here. What we care about is adjusting how much air is up here. We want this distance here to be 19.5 centimeters. If we get that to be 19.5 centimeters, that will be the pitch that we need. That will give us an A. Now, that might be a little bit big for a lot of bottles. So if we do the same process with 880 hertz, So let me see here. 343 divided by 880 will give us a wavelength of about 39 centimeters, give or take. And if we divide that by 4, now we're talking about 9.7 centimeters. So this could also be, if our pitch is 880 hertz is our frequency, that height could be 0.0974 meters. Okay, so let's try this out and see if it works. Now you probably noticed that the measurements that I had to get a perfect A were a little bit shorter than what we calculated here. And there's a reason for that. This velocity right here, 343 meters per second, isn't always the speed of sound. Even though we take it as that, it's usually close enough. But it turns out where I live, I'm a little bit above sea level, which means the air pressure is a little bit lower than it is at sea level, which means sound travels a little bit slower. So because of that, this 343 is actually probably a little bit lower than that, probably in the 330s somewhere, which means this number, the wavelength, is a little bit less, which means that this number is a little bit less, which means that this distance we calculate should be a small bit less than what we actually calculated. And it turns out it is. We find it, instead of being about 19.5 centimeters, it was somewhere around 18, and instead of being almost 10 centimeters, it was between 8 and 9. But pretty close. And yeah, you can design your own instruments and your own pitches. You can tune it by varying the amount of water in there, and you can get whatever pitch you want based on how much water you put into your bottle.